Hello everyone and welcome back. My name is Mr. Cobalt, and in this video I'm going to be going over how to do a weak acid strong base titration problem. And so in this problem here, as an example, you're given a 40 milliliter sample of a 0.100 molar HNO2 solution, and you're titrating it with the strong base 0.200 molar of KOH. And then you're asked to do a few things. The first thing you're asked to do is find the volume required to reach the equivalence point. Okay, so what is the equivalence point? The equivalence point is where the moles of the base added is equal to the moles of the acid you are titrating, and vice versa if it was the other way around. So the first thing we need to do is find the total number of moles in the acid. And so we're going to use the volume and the molarity to calculate the moles of acid. So we got 40 milliliters. So we got to convert that to liters, right? So you have 40.0 milliliters over 1. Use molarity as a conversion factor. So this is moles over liters, but you have to convert milliliters to liters first. So you're going to say we have 1,000 milliliters on the bottom and 1 liter on top. So milliliters cancels out. And then you are ready for your molarity. So use the molarity. And I should be writing HNO2 here. So this is HNO2, HNO2, HNO2. So that way we know what we're talking about. We don't lose track of our substance. And so here the molarity is going to be 0.100 moles of HNO2. And it's going to be 1 liter of HNO2 solution. So the liters cancels out, and you have moles, and then when you calculate that out, you get 4.00. We're going to do 4.00 times 10 to the negative 3 moles of HNO2. So that's the number of moles that we have of our acid. Well, to reach the equivalence point, you have to add the equal number of moles of your KOH. That's going to be the same number of moles of our KOH. So we need to add 4.00 times 10 to the negative 3 moles of KOH to reach the equivalence point. Because that's what it just means to be at the equivalence point, is that the moles of acid equals the moles of base. Or in other words, another way to put it, the moles of H plus ions that you're adding must equal the moles of OH minus, the hydroxide ion. And the reason I put it that way is because sometimes you might have a base with more than one hydroxide ion in the formula. Or you might have a polyprotic ion, a polyprotic acid. So just be aware of that. Okay, so we got our moles of KOH we need. They're asking for the volume. They gave us the molarity. So we'll just use the molarity as a conversion factor to convert to liters, or the volume, and we'll convert to milliliters. So we have our moles. We'll start with that. 4.00 times 10 to the negative 3 moles of KOH over 1. And then what we're going to do is we are going to convert this, use our molarity. So we have 0.200. So that's going to be moles over liters. We'll put moles on the bottom. So it's 0.200 moles of KOH over 1 liter. So moles of KOH liters of KOH solution on the top, and then multiply by conversion factor to get from liters to milliliters. So 1 liter of KOH solution on the bottom, and we'll have 1,000 milliliters of KOH solution on top. So liters cancels out, and now all we need to do is calculate the number of milliliters, and when we calculate that out, it comes to 20.0 milliliters of the KOH solution. Okay, so that is part A. So now for part B, it says, what is the pH after adding 5 mils of the KOH? So let's erase the board here. Okay, so here we go for B. They're asking for the pH after adding 5 milliliters of KOH. So remember, KOH is a strong base. And so what you need to do is you need to calculate how many moles of hydroxide ion you have added. And that hydroxide ion is going to completely react with the weak acid that is available. So you got to do like an addition stoichiometry table first to figure out at the end of that reaction how much acid you have left and how much conjugate base you have. And then you could use that to figure out the pH of the resulting solution. And then with that you could use the Henderson-Hasselbalch equation. Okay, so here we're going to use 5 mils, so we got to do 5.00 mils of KOH solution over 1. We're going to have to convert this to liters, so 1,000 milliliters of KOH solution over 1 liter of the KOH solution. Liters cancels out, and then we can use the molarity. So again, liters is on the bottom, so 1 liter of KOH solution yields 0.200 moles, 0.200 moles of KOH. Okay, now all we need to do is calculate the number of moles, and that comes out to 1.00. So 1.00 times 10 to the negative 3 moles of KOH. Okay, so now we have moles of KOH. So that's the number of moles of KOH, which is also the moles of OH, since it's a 1-to-1 ratio. So now we do our table. So here we have before adding. So if we write down the table, we have our equation, OH minus plus HNO2 is going to go to water plus NO2 minus. So that's our acid base neutralization reaction. And so what we need to do now is we have to do our addition or stoichiometry table. So before adding the base, we had 0 base, and we had for HNO2 we had what did we calculate that to be? 4.00. So in part A we calculate this to be 4.00 times 10 to the negative 3 moles. Okay, so that's the number of moles of HNO2 that we have to begin with. We're ignoring water, and we essentially have 0. Oh wait, that is going to be right 0. So because this is before the reaction, so essentially this is going to be 0. It's not quite 0, but practically it's 0. So that's before we add any base. And then when we add the base, so now we're going to add this amount of OH. So we add 1.00 times 10 to the negative 3 moles of the OH. We're not really adding any more of this or this. So then what happens is this OH is going to react completely with the HNO2 here. So you're going to have to subtract out from here this amount. So after adding, all of this is going to react with this. So that's going to become 0. This is going to become, we're going to subtract this amount because this OH, this amount of OH is reacting completely with the same amount of HNO2. So 1.00 times 10 to the negative 3 moles is going to have to be subtracted. So this becomes 3.00 times 10 to the negative 3 moles. So we have that much left. And then because it's a 1-to-1 ratio, the amount that reacted with this forms the same amount here. So we get on this side 1.00 times 10 to the negative 3 moles of our NO2 minus. So now that we have figured out the amounts that we have after the adding of the 5 milliliters of KOH, now we can use the Henderson-Hasselbalch equation. And the reason for that is because the reaction, the ionization of your KNO2, the Ka, is much smaller than the original amount of the concentration of the acid itself. Okay, so now we're going to use the Henderson-Hasselbalch equation to figure out the pH. So the pH is going to be equal to the pKa plus the log of the concentration of the base over the concentration of the acid. So what's the Ka value? Okay. Okay, so the pKa is 3.34. So that means pH is equal to the 3.34. And you would get this from the Ka value of KNO2 that you would look up, take the negative log of it, and then that would be plus the log of, and then we've got the base and the acid. So the concentration of the base is 1.00 times 10 to the negative 3, and the acid is 3.00 times 10 to the negative 3. Okay, and so this would be equal to 3.34 negative 0.48 for that. And then you add this together and you finally get 2.86. So 2.86 would be the pH once you add 5 mils of the KOH. Okay, so that's part B. Part C I'll do in the next video. Thanks for joining me. Thank you. See you next time.